6 in decimal, how would you represent it in hexadecimal? 2e, exactly. Okay. The quick way to do it, to do the conversion, is to find the closest power of 4 to 46, and this time is really close because it's 3 times 16, right? So 3 times 16 means it's 30 in hexadecimal, but we are missing 2. Okay, this is 2 less than 30, so you step backward. If you take 1 away, it becomes an F. If you take 2 away, it becomes an E. So 2E is the hexadecimal representation of 46. Very good, good job. The other quick way to do it, depending on how good you are with binary numbers, is to look at the binary representation, because 1110 is the least significant nibble, which is E, and then we have 10 left for the high nibble, and 10 is 2 in hexadecimal as well as in base 10. So that's the other way you can get to 2E, in this case. Are there any questions about this slide? One quick and easy way to understand base conversion is simply to imagine that instead of the currency system that we have. Now I have to say that the currency system in the United States that we have is really not intuitive at all. Okay, and yet how many people here think that you can work at Walmart or McDonald's and be able to handle the change to a customer using the least number of bills and coins? Okay, I don't want you guys to give someone like thousands of pennies. Can you guys handle that? Okay, if you can handle it, you already know base conversion. You know more than base conversion, because base conversion is nothing more than imagining that our money system has 1, 2, 4, 8, 16, 32, 64 dollar bills, and on the other side we have half dollars, quarter dollars, eighth dollars, 16th dollars, and so on. So if you know how to deal with that, you know base conversion. It really is that simple. Are you guys kind of convinced? All right, very good. So next slide talks about adding. Now adding is pretty easy because we only have 4 possible cases. Actually adding, subtracting, and multiplication only have 4 cases. They all have only 4 cases. In this case, the first case is the easy one. 0 plus 0 is 0. We talked about this last time already, but I just want to kind of go through the notes to make sure that you guys know where to find that information. 0 plus 1 is 1. Okay, we know that. 1 plus 0 is 1, so they're all pretty easy. 1 plus 1 is 10 in base 2. It's a little new, but it's not really that difficult to understand, because it's kind of like 5 plus 5 in base 10 is 10 in base 10. It's because the quantity of 10 is more than what a single digit can represent in base 10. In base 2, a single digit can only represent 0 and 1. So the quantity of 2 requires 2 digits to represent it, and that's why it's represented as 10. Any questions about that part? The questions? Okay. So in this case, we can also look at this as 1 plus 1 is 0 with a carry. Okay, that's a much better way to look at this, because that will set us up to handle multi-digit addition. The rest of this slide uses this one single example. 0, 0, 1, 0, 0, 1, 1, 1, add plus 0, 1, 0, 0, 1, 0, 1, 1. So we want to figure out what is the actual sum between these 2 binary numbers. We start with a carry. This entire row here are carries. But we start with a single carry here because this column is the least significant digit. There's nothing that can generate a carry for this particular column. So that's why we always start with a 0 of carry for this particular column. So we first perform the first addition of this column, the least significant digit. We have we have 1 plus 1, which turns out to be a 0 with a carry, right? And then what we do is we have 0 plus 0, which is a 0. I know most of you do not carry out, decimal addition, using a separate row for all the carries. But that really is just a way of representing the carry. I just chose to do it this way because it is more explicit. But it really is not any more different compared to the way you do decimal addition. Are we doing okay so far with this example? Okay. So I'm just going to do one more column, and then you can read the rest of this slide. So after we handle the first or the least significant digit, we can now handle the second least significant digit, which is this one. 1 plus 1 is a 0 with a carry. And then we have to handle the other one, the other part, which is the partial sum and the carry from the less significant digit. So we have 0 and 1. 0 plus 1 is 1. And then next we handle this part here. 1 plus 0 is 1, so you put a 1 here with no carry. 1 plus 1 is 0 with a carry here. So you can see how this goes on. Are there any questions about how to add binary numbers? Yes?
Why do you call the far right column the least significant digit?
Because it carries the least significance. The rightmost digit tells me how many ones we have. And that's why it's the least significant digit. The next one tells me how many 2's we have, and then how many 4's we have, and so on. So it's just called the least significant digit in this case. Or in this case, I can call that the least significant bit, otherwise known as LSB, least significant bit. Okay. Are there any other questions? That's a good question. Yep.
I'm a little confused. Like what you have right now highlighted, is that going to be a 0 or a 1? Why?
That is going to be a 1.
Why?
Okay, I can explain that. Okay. So what you do is you can kind of imagine, it's actually done here, but I wanted to kind of show you how it's done. So we have we have 1 plus 0, which is a 1, right? But then we also have 1 plus 1, which is a 0 with a carry. In other words, you have 2 chances of generating a carry for the next digit. And it is impossible to have both additions generating a carry. You can only have up to one of the adding process to generate a carry. Okay. All right. So are we still doing okay so far? So when you read this entire thing, it has a final result here. And I will give you homework assignments where I will ask you to add binary numbers. Most of you will think, oh, that's easy, my calculator can do that. Except I will ask you to show it like this. So your calculator may not be able to do it. And some people will say, but Tech, I can write a program to generate a form like this. You know what? If you can write a program to do it, that's fine with me. Because if you can write a program to do this, it shows me that you already understand the concept. Yep.
I was gonna say, the way you're doing it's sort of confusing to me. Can we just show you that we do it by carrying like regular addition? When you carry a 1 in regular addition, it just goes up.
Oh, putting it up above the other one instead of doing
You can represent it that way if you want.
Okay.
But throughout the semester in this class, I'm going to use this method to show addition. So you will have to kind of get used to this format because I'm using this in the class. But when you are doing it, you can use it. You use your own method. All right. Next slide. Subtraction. Subtraction is actually not any more difficult. It really should not be any more difficult than addition. 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 0 is 1. Okay, so those are all the obvious cases. 0 minus 1, I would call that 0 minus 1 is 1 with a borrow from the next bit. Okay, which is the same thing as 0 minus 3 in base 10 is 7 with a borrow. It's no different from that concept. So in this case, if I apply all this stuff here, then the least significant digit becomes 0 minus 1 is 1 with a borrow. And then we have 1 minus 0 being a 1. Moving on to the next digit, we have 0. We have 1 minus 1, which is 0. It doesn't generate a borrow yet. 0 minus 1 is a 1 with a borrow. And then we move on to the third column from the right-hand side. We have 0 minus 0 being 0 with no borrow. 0 minus 1 is 1 with a borrow. So that's how we carry out multi-digit subtraction in binary. Any questions about multi-digit additions or multi-digit subtraction? Yep.
When we borrow, do we replace the one with a 0? When we borrow.
When you borrow, it becomes a 1. If you do not borrow, it is a 0. Okay, let's do an example. Let's go ahead and do a live example, digit by digit. Okay, so let's go ahead and do it. Use mouse pad. All right, so we'll start with. Okay, let's not deal with anything that's too complicated. We'll deal with 1 1 0 0 minus 0 1 0 1. And these are all in base 2. So I'm going to do the same thing here. We have another subtraction here. This is basically an entire row of borrows. So fill it up with space, and then we can I can use the override mode to handle this. All right. So we'll just have to kind of remember the four cases that we have talked about earlier. 0 minus 1 is what? 1. Does it have a borrow? Yes.
Yes.
And then we have an implicit 0 here. 1 minus 0 is 1. Is that okay? Then we have 0 minus 0. 0 minus 0 is a 0. Does not generate a borrow at this point. 0 minus 1 is a 1 with a borrow. So just like with the case of addition, having 2 chances to generate a carry, you have 2 chances to generate a borrow in this case. All right, moving on to this column. 1 minus 1 is a 0 with no borrow. 0 minus 1 is a 1 with a borrow. Over here, we have 1 minus 0 being a 1. It does not have any borrow. 1 minus 1 is a 0. Since we did not have any borrow, in this case from both subtraction, we have a final situation of no borrow from the next digit either. Now this last borrow doesn't seem to be important, but it actually is very important. Later on in the class, that becomes our carry bit, but that's kind of, we have another week or so at least before we get to that instruction. Is that okay? Does everybody understand how that works? Okay. Yep.
So what about when the bottom number is bigger than the top one? When you get a negative answer, I guess.
When the bottom number is greater than the top number?
Yeah.
Okay, let's go ahead and deal with that situation. Okay. So we have, let's say we just flip it, right? 0 1 0 1 minus 1 1 0 0. So we'll try to find out what happens here. So the same thing, I give it, this is the partial difference, and then these would be the borrows, and then this is the final difference. We always